So one of the things that Python does very well is all these containers. So we have learned basically two containers. One was lists, and the second one was sets. And today we are going to learn a third one called dictionaries. And dictionaries are like lists and sets combined. Now, how many of you remember that I wrote this program and it was super slow, and then we changed to using sets and it was very fast? Do you remember this? Kind of? Okay. Now, we are going to talk about why that is today. And it's going to involve this scary sounding word called computational complexity. Oh yeah, it's a big word. But now you are computer scientists. You should not be afraid of words like this. All right. So let me try to explain a little bit what that is, and then we will see why this is very important as we are solving the different problems. It's going to be similar to what we did, but we are going to add more complexity. So lists are basically containers that are stored in such a way that you can index individual items in them. But the way that you can find something in a list is to find the index of something that you want. So I'm going to have different, just for a change, different strings like sun, moon, river, leaf, snow, etc. Okay? Now, if you wanted to get something inside the list, you wanted to get sun, or you wanted to find if sun is stored in the list, there is no way to check if sun is stored in the list other than to go and look at every single index, right? You know how to go through the indices in the list, but you don't know how to go through the values in the list because there is no mechanism for it. So if you want to find what is in location 1, you can say, okay, print what is in location 1, which happens to be moon. If you want to find what index something is stored in, let's say what index is leaf in, index of leaf, okay? There is a function that does that, but the way that function works is actually going through and checking one by one every single location in the list, right? There is no find the place of leaf. There is only indices that are 0, 1, 2, 3, or you go through every index and find what is stored. So you basically go through 0, 1, 2, 3, and then find that, in fact, L of 3 is equal to leaf. Then you return, for example, 3. Okay? This is basically how lists work. Lists are great if you have things that naturally have an index 0, 1, 2, 3. For example, in the exam we had months. For months it's logical, right? The natural index is also the real index. The ordering is the same. But for some things this is not true. So what you really wanted to do was continuously search for things by their value. That, what I really want to do is find if sun, moon, river, leaf are stored in the list. Lists are not great for doing that, okay? So let's say this is called a search problem. So if I want to search for value in a list, like river is in L, the only algorithm that I have is go through every single item in the list and then check if it is equal to. right? So because of that, we care about how many things are in a list. So if there are 10 items in the list, how many items do I need to compare to find if river is in the list? What is the best case scenario? It's the first one. So in that case, I have what? What is the worst case? The last one. So that means I actually have to check, is it equal to the first one? No. Is it equal to the second one? No. Is it equal to the third one? No, right? So every single time you compare, there's a little cost. And that cost adds up. And it adds up in such a way that if you, let's say, if each search takes about 1 millisecond, it's probably less, but let's do 1 millisecond. And if you have to compare 10 items, it's going to be 10 milliseconds, right? What if it is 1 million items? 1 million trillion. Right? So if it's 1 million items, it's 1 million milliseconds, right? So generally, you don't really care what the number is. What you care is whether it scales as a function of how many items. So instead of how many items, 1, 10, we are going to use a variable like n. So if you have n items, I have roughly n comparisons. So it appears that that seems to be logical. How can you do less than n, right? How can you not look at every item to find if something is stored like that? So this is where the programming and computer science comes in. So in fact, I can do some homework before. Instead of storing things at 0, 1, 2, and 3, I'm actually going to have a slightly different method for storing them. So I am going to take whatever is stored in, whatever I'm going to store in list, but I'm going to store them in a new data structure, which we call sets. So in sets, I'm going to do something slightly different. I still have location 0, 1, 2, 3, 4. But I'm not going to just store these values anywhere. I'm going to take, for example, sun. It's a string, but I can take a string and I can process it in various ways. So for example, I can take the values of these strings, add them, get some number. There's actually an ASCII code for all of them. Then I get some value, and then I apply some function. Let's say I take the values for these, and then I apply, so let's say this goes up to 5, a hash of 5 mod, so take the value, add, then do mod 5, which will give you a value between 0 and 4. And then, if the value maps to, let's say, 4, then I'm going to store the value in location 4. So I'm going to take some value, which we call hash. That returns me a value between 0 and 4. Let's say hash of sun is 4. Then I'm going to put sun right here in 4th location. So it's not really ordered in any way, because it's not the order I inserted in. It's not alphabetical order. But the nice thing is that if you ask me whether sun is actually stored, all I need to do is take sun, apply the same function, go to location 4. If location 4 has sun, I know sun is there. If not, I know it's not there. Okay? So if this is kind of confusing, that's okay. This is all new to you. The point is that I'm doing something in advance. I'm changing the way I store things. So in the sets, I don't actually store them in random order or sorted order. I actually store them based on their value. So to find if sun is in a set, of values. I don't really need to go and check every single value. I only need to check one location, the location that would have sun. Okay? So I only need to do one comparison. And this will not change if I'm storing 10 things or if I'm storing 100 things. So regardless of how many things I store, I still have one comparison to check if something is stored. And you can imagine that this gets to be very important as you start adding things. So this is why we are learning about these containers, because which container you use will have a big impact on how fast your program runs. Do you ever use any product in your life where you are frustrated by how slow it is? Yes? Do you? I'm very frustrated with my DVR, just like it takes forever to go from screen to screen. It just means it's written by a bad programmer who doesn't understand complexity. Okay? So we want you to be the better programmers, that's why we are talking about it. Okay? So what have you learned so far? I know it's a lot of startup, but this is an important point. So we have learned that how you store something is very important in figuring out how long it takes to look it up. So we had basically two things that we know about. So one was value in list, and how long it takes really depends on how long the list is, right? The longer the list, the longer it will take for you to find something in it. So this depends on list size. So from now on, we are going to use list size of n. And instead of saying depends on list size, I'm going to use order of n. Okay? Order of n just means that if I increase the list size twice, my program is going to be at least 2 times longer. Okay? So this basically means that depends linearly on list size. Okay? So that means if you have m, which is 2 of n, that is like 2 times order of n. Okay? Generally, you don't care about the 2, but that's kind of easy to start thinking about. Whereas if we do have value in set, it does not depend at all on the list size. You can store one thing, millions of things. It still has roughly the same cost. So does not depend on list size, which is what we write is order of 1. N is irrelevant. Okay? So the point is that order of 1 is the gold standard. If you have a program that uses order of 1 constructs, that is great. But it is not always possible. And order of n means that as you get longer and longer lists, it gets worse. Well, the point is that that's not the end of it, of course. There's a lot more that happens. Let's see if I can find this. As n grows longer. So, you will see things like this in the next class. But, how long you are going to wait for something to execute, it really depends. So order of 1, you don't see here because it doesn't depend on this. It's always the same number of operations. If you have order of n, which is the green line, it means that as you have more items, you are taking longer and longer, right? If you have more things, it takes longer to do the same operation. But then we are going to see if there are things like order of n squared, which is this thing. As you have more items, things get bad, but much faster. Okay? What is order of n squared? Anytime you write a double loop, you're writing an n squared operation. Okay? And n squared is bad. This is why I keep telling you to be aware. And this is, now that we passed exam 2, we are going to be much more aware of complexity of the things that we do. So let's write a simple algorithm to process this file, hanks.txt, and then we will talk about complexity, and then even do more interesting things by going beyond lists and sets to actually dictionaries. So this file is exactly like the IMDb file that we had. It has name of an actor. It has the movie that they were in, and then this is the year of the movie. So the last time we went through IMDb to find all the movies for an actor. Today, we are going to do something much more complex. We are going to find for each actor how many movies that they were in, and then we are going to find people who have the largest number of movies. So we are now going to write a much more complicated program. So let's try to do this. You can do the same thing with IMDb, but it will never end because it's so slow, because it's such a large file. So we are going to start with Hanks. And I want to find for each actor how many movies that they have started. Now, you have many different ways you can solve this. And we are going to write different solutions and look at how good each solution is. So let's write a very simple solution for each line in the movie. Okay. So what I can do is maybe I can have a data structure like list of lists. Something like actor and number of movies. And let's call this num movies. So for each line in the movie file, I'm going to find the index of the list that has the current actor. Add 1 to the number of movies. So this is the kind of algorithm that I want to start with. What are the things that I need to do? I need to read a line from the file. I need to extract the movie and the actor, and then find where I stored them in the list, and then add 1 to it. What happens if they are not in the list? If not, I need to add a new item into the list, right? Initialize it at 0, then I will add it, right? So let's write this very simple one, and then we will go from there. So I will try to go through how I write such programs. So as always, I start from what my program does. This is what my program does, right? So I'm going to have to open the file, read line by line. Okay, this is the for loop. And then find actor index, and then add 1 for movies. Okay. First, I need to basically have a variable that keeps track of this. Let's call that number of movies, which currently has no information. Then I need to open my file. And whenever I do this, I immediately save it so that I know it's in the same place as hanks.txt. Okay. Now, for line in F, I'm going to have to extract information from this. So what I'm going to do is I'm going to write a function to do that so that I can reuse that later on. So I'm going to just write a function called Parse Line. So since after I've done this, what was the delimiter? It's this. All right. So actor is going to be M of 0 strip, and movie is going to be M of 1 strip, and then year is going to be int of M of 2. And then I'm going to return actor, movie, and year. Okay. So for line in F, I'm going to find A, M, and Y, which is parse line. Okay. Next, I need to find which index this actor is stored in. So I'm going to write a function for this. So I'm going to find actor in number of movies and A. I'm going to write a function to do this one. Okay, so you see that I actually am passing the list, so I don't have to look up where the list is stored and whether it's initialized. I just want to do all of that in my main program, and every function has no global variables. I pass whatever I need to. So basically what I'm going to do is this. So for each actor, so for each item in here is basically a list of actor and number of movies. So if num movies of I of 0 is the actor, then I'm going to return I. Okay? If I find the actor, I'm going to immediately return. I don't need to go through the other items in the list, right? So I don't need to go to the end of this. What happens if the actor is not in the list? So what will happen to my program in this case? Will my function return something? No, right? Because it will go through the for loop that's not there, so I have failed. So if I have failed, though, I still want to return something, so my function works the same way no matter what the input. So what I'm going to do is I am going to append. If I've come this far, that means this actor is actually not here, right? So I'm going to append the actor A, a list of actor A and 0, right, with 0 movies. And I am going to return the length of num movies minus 1, because that's the last item I added. So now I have this very simple function, but it does actually return how many things there are. And then immediately I get actually an index no matter if it's in or not. And then since I have an index, I can now add 1 to this. So num movies of IDX, add 1. Okay. So the program itself is simple, and it kind of has a few helper functions. And maybe it is correct, but you have to test it to see. If you really want to do it slowly, you can actually kind of start with, you print the line, you print num movies, and then you can actually put a raw input so that you can see how it is going. If I'm convinced that this works, then I can continue. Okay? So, for example, the first thing I read was Jim Hanks with some information. Immediately I realized that maybe I should not do like this whole thing. I should just print the actor so it's easier. I can have smaller things. Okay? So I have Jim Hanks. When I run it, it gives me an index because actually this is a list. I wanted to have a list of lists. So this should actually be 1, right? So the 0th item is the actor, the 1th item is the index. Okay? So now it's telling me global actor is not defined. This one actually fails, right? Because this should actually be A. You see, my programs also always have bugs. This is the way it works. All right. Now I have, I've seen 3 things with Jim Hanks. Now I see Colin Hanks. So I add 1 for Colin Hanks. I have Bethan Hanks, so I added 1. So now I have Tom Hanks, I added 1. I have Zach Hanks, there's a lot actually. Okay, now I have another Colin Hanks. So that should be now 2. So it seems to work, right? So by some, with some hope that this is correct, so I am going to get rid of my debugging code. And if you wanted to, you can print Now, for example, if you wanted to find how many movies for a single actor, you can do the same thing. You can say, okay, name, enter a movie. Let's say enter an actor. And then I find IDX, find actor, num movies, name. And then I will say, %start in the movies. I'm already regretting that my name of my variable is way too long, right? So this is the first thing I will do is I will rename that variable later. But regardless, here it is. So if you wanted to find, for example, Hanks Tom, it will tell me that it started in 41 movies. And you see, since I wrote this nice function to look up somebody, I didn't have to actually write a lot of code. I can just call that function in many places. So my question is, what is the complexity of this problem? Okay. So now it looks pretty simple. But let's look at what we do. So this is the main problem, right? So this is what we do. For each line in the file, okay, and I can tell you how many lines there are. So there are 68 lines. Okay. For each line in the file, 68 times, I first find the actor, however many actors there are, and then I return it to you. I add 1, and eventually I'm done. So basically, my problem is as follows. So for each line in the movie, for each actor in the list, find the index. Okay? So in fact, my program is a double loop, right? Because for each line, I do a second loop for each item in the file. So in this case, it happens that I have fewer actors than lines, but generally, if you had 1 actor for each line, it would be n for actors and n for lines. It's actually n squared, n times n, right? So if you want to kind of understand what I mean, you can actually compare this with IMDb data. And if you were to do this, this will take forever because this is actually going to take you a long, long time to do this. If you want to see the progress of how this is going, here it is. So let me add I do this all the time. If you want to see how slow this goes, if you use the real data, it is pretty slow. So this is what we call an n-squared solution, because searching the list is n operations every time I need to search the list. And I need to do that for every line. Let's say that's also n. N times n is n squared. And the one thing remember is n squared is slow. You saw that big line, right? So it's very slow. All right, and I don't know. Okay, let's do Hanks here. Okay, so this one is better. Now let's do a slightly different solution, which doesn't do it like this, but it does it in a more computer sciencey way. So what I'm going to do instead is I'm going to first read everybody into a list. I'm going to basically have Tom Hanks, Tom Hanks, Tom Hanks, Tom Hanks, Tom Hanks, but it's not, since it doesn't actually arrive in the sorted order, I'm going to first put them in a list, then I'm going to sort it. So I'm going to take all this and create a new solution. Okay. But it's going to be a substantially different way of doing things. So let's get rid of this. Let's get rid of this. This is the same. Okay. And I'm going to have a very simple item. So what I'm going to do is I am not going to look for the actor every single time. I am not going to add one. I am just going to take all the information I find and I'm going to append it here. Okay. So it's going to look something like this. Basically, I'm going to put all the names in a single list in the order I find them. So there are 68 lines, so there's going to be 68 items in this list. But now, I am actually going to sort this file. Now, when you sort this file, something interesting happens. You see that, how many movies do you think Hanks Batten had? Are we confident to say Batten Hanks had only one movie? I have sorted this list, right? So if there was another Hanks Batten, it would be right after this one. How about Brad Hanks? How many? One, okay? How about Colin Hanks? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's it, right? Since I sorted, the same name will appear consecutively, right? So I don't need to really go and check everything. I need to now go through this list one time to find all the counts. So after I sort, it's actually quite easy to find how many movies a person has. I can actually construct that very easily. So what I can do is I can do the same thing as I was doing. And then I am now going to go for I in range length of info. So actor is going to be okay. So this is the current actor. If it is the last actor in my file, then I am going to be able to add one to it. So if actor is equal to now movies of the last item 0, then I am going to add 1 to it. Else, that means this is a new actor. I am going to first add 1 with this actor and 1. Right? I will keep adding 1 to the last actor. Unless I find a new actor, then I'm going to add that one. Are you with me so far? Just a single pass. Now this program obviously is going to fail. So if I were to run this, it will give me an error. Can you see why? Okay. Here, I'll give you a second to think about this. All right, any guesses as to why this fails? That is true. When you first start, is there anything in the non-movies list? There is no actors, right? So you're trying to find the lost actor, but there is no lost actor. So you cannot actually index that value. So anytime you have this kind of a loop, you really worry about the first thing that will happen, right? So how do I make sure that it doesn't happen? Well, I can actually probably put the first actor in here. So I can put info of 0 with 1 movie. And then I can start iterating from 2. Something like this. Instead of really starting from the last value, I start iterating from the second value. Okay. And then you can test to see if the rest works the same. So that seems to work the same. So now, let's look at what the complexity of this program is. Okay. Yes?
Why is it great to
It should be 1. Because I forgot that it's 0 indexed. Thank you. Because I actually skipped 1. That was your question too? Yes, thank you. Anything else? Okay. Now, my claim is that this is actually a much faster algorithm than the first one. Instead of doing it the way that I did, I actually read line by line. But then, for each line, I didn't have a search. I just kept adding things to the end, which is actually very fast, because I don't have to check anything. So I only did 1 pass, which is order of n. Then I had this thing called sorting. Now, sorting we haven't learned, but we will actually do. Sorting is actually not very cheap, but it is not as bad as n squared. So instead of order of n, this sort is going to be somewhere slightly cheaper. So it's going to be order of n log n, which we will see later on. Yes? I can't hear you. I can't hear you. What about info? I just use it as a kind of secondary thing. I just put stuff in it. When I'm done, I don't care. Because the thing that I really wanted to construct was this. But appending something to a list is very cheap, because you don't actually have to search. You know where it ends. Okay, so let's do debugging after class. Let me just go through this material first. So, so if you want to see if this is actually faster, I can do this. And I'm going to do the same thing that I was doing. Now I'm doing the same thing with IMDb data. It seems to be still slow. It's actually killing my computer here. But it does seem to work, right? It takes a little bit of time, but it actually works. In the other one, I would get no information. Right? So this is kind of the distinction between having an algorithm that is very, very, very slow, having an algorithm that is okay, to an algorithm that is lightning fast. So that's what we are going to do next. Next, we are going to learn about dictionaries. So the dictionaries are basically a hybrid between lists and sets. In lists, you index by the location. So lists are indexed by where you are storing information. Dictionaries are indexed by the content themselves. So dictionaries are basically indexed by keys, but your keys can be anything. Can be anything that can be put in a list, in a set. Okay? So let's try to see some examples. So when you're creating a list, you use square brackets. When you're creating a dictionary, you use curly brackets. That means you're creating a new dictionary. So this will create you an empty dictionary. There is nothing in it, so but instead of appending items to it, which is what you would do with lists, you actually put information by describing what the key is. So the key is anything that is hashable. So let's say we create a dictionary of strings. So for example, for actors, I am going to have a key called Tom Hanks. Okay. This absolutely does nothing because this is actually a location. But in that location, I'm also going to store how many values there are. And how many were for Colin Hanks? Let's say 11. Okay. So there is no like add an item. There is adding a value at a certain key. Whereas in lists, the key itself is always incrementing by 1, which is the index. Whereas here, you have a completely different way of doing the same thing. So my dictionary is now a collection of key and value. So I have two keys. One is Tom Hanks, the other one is Colin Hanks. But for each key, I can look up something. So previously we had a list and your keys were things like 0, 1, and 2 were keys, and you could store information here like A, B, and C. For a dictionary, this is a little different. Your keys can be anything, so you can have cat, dog, and pig, if you want to store how many dogs and cats and pigs you have. And then the values themselves are what you store in that cell that is indexed by the given value. So this could be 4, 5, and 1. If it's my neighbors, it's actually 3 dogs, 1 cat, and 1 pig. So the distinction here is that you have keys that you can assign other than just 0, 1, and 2. If you really wanted, you could actually use 0, 1, and 2 as dictionary keys. So you can have d of 0 is equal to 1, d of 1 is equal to 2, d of 2 is equal to 3. This is a very boring dictionary, really, because it just doesn't store anything interesting. And you can have any combination of keys, like in fact, when you have a dictionary, the keys of the dictionary themselves are stored as a set, exactly as I was describing in the beginning of class. You take the value, you apply some hash function on it, it gives you some address. And then you put that in that address, you store the key. Now you also have, for that key, other values. So you can generally see what the keys are for a dictionary. You cannot just add a key. There is no append function. But you can create a new key by just indexing it. So you can say d of address and your value can be anything, and the key can be anything, except that there are a few limits. So your keys are anything that is hashable. Okay. So for the purposes of this class, think about hashable things as integers, strings, anything that has a simple value. What are the other things that we know are simple values? Tuples. I think that you can have tuples as a key. Let's try. Okay. You probably can have floating point numbers as a key, but it's a very bad idea because of precision loss. So generally, you are not required to. And I believe you can even have a Boolean as a key, which is a very stupid idea, but you can. So anything that is simple value, you can have a key. Boolean and what was the other one? Let's not put floats. But you cannot have complex values. You cannot have lists as a key. It says that list is unhashable. You cannot index with a list. You cannot index with a set. So anything that is simple value can be a hash. So we have seen examples of this. Don't use Booleans for that, but you can if you want to. But values can be anything. What you put on the right side can be anything. So you can store anything as a value. Values in a dictionary can be anything. In fact, for example, if I had actors here, instead of storing the number of movies, I could store the names of the movies. So I can store the names of the movies as a list, such as some of the better movies. You've Got Mail, it's kind of. All right, but it is. That's valid. I was trying to find Joe versus Volcano. Ooh. All right, I'll put it for you. He was not in Sharknado. I have watched all of the Sharknadoes, and I can tell you that was not. Okay? So now you have a dictionary where you have one key that points to a list, the second key points to a number. It is your responsibility, whatever you want to store, as long as you can get it out. But generally, you don't do this. You generally have the same data type for keys and the same data type for values because you're using it for a single purpose. And you can do all sorts of other things. That's stuff I never do, but I will show them to you. I never really remove things from a dictionary for the purposes that I do. But if you really want, you can remove a certain value from a dictionary by deleting it. So you can delete a certain item, certain key by del. You can pop a certain item. So you can pop, for example, 2. That will basically take the value that is stored at 2, return it to you, and then remove the key also from this. Yes? You can also do something called pop item, which will basically take a value, remove the value and remove the key and the value, but as a tuple. I guess not true. All right, so one of them randomly. Say it again. Okay, so these are not necessarily super useful. And the things that I very frequently use, give me a second, that you get the keys from a dictionary. But the keys returns you the set, not the set, but the list of keys. You can also get the values from a dictionary, which is the actual all the values as a list. Yes, what's your question? Okay. So now here's a very important part. Okay, this is the most important part of this lecture. Okay. So do we have any questions about dictionaries so far? We are going to have a whole other lecture on Monday. Yes. Whole item just returns one random value. Yeah. Yes.
You have a dictionary, and let's say you have a function that adds things to a dictionary. Can you call specific items from a dictionary?
You can call specific items by basically addressing them, but you cannot return the 0th item because there is no ordering. Okay. So the keys itself in a dictionary are stored as a set. So that's the most important part. Okay, so keys in a dictionary are stored as a set. So if I were to have a dictionary, for example, Tom is in 41, Colin is in 11, and Brad is in 1 movie. Okay. And if I were to ask, if Tom is in actors, what this is asking is if Tom is one of the keys, right? Not one of the values. If you want to find if a value is in the keys, you use the same exact problem. But what that is doing is actually looking for Tom in the keys, which is stored as a set. So the lookup for this is order of 1 because it's a set operation. So finding if Tom in actors, which means if Tom is in the keys for dictionary actors, then I'm going to print actors Tom. Okay. This operation here is a set operation. So basically, this is equivalent to a set lookup. As a result, it is also order of 1, which is like we were talking about before. So what I want to do is, in the remaining time, write the same program that I wrote in 2 different ways, but now I'm going to write it using dictionaries. So for example, I am going to take the same exact thing that I was doing here. Okay. But I'm going to skip this step altogether because I don't need to find the index of the actor at all. That operation is gone because I can just check if it is in the keys, right? So if actor is not in keys, Adam her with 0 movies, and that's what I'm going to do. And I'm going to change this. I'm going to have the actors as a dictionary. And generally, when I have a dictionary, I write what the keys are and what the values are. Okay? So I'm going to basically have a completely different way of doing things, but I don't really need to do this anymore. So I'm going to have the solution 3.py. Okay? I don't need to look up things anymore because that is given. I am going to have one called actors, which is a dictionary. Okay. If A is in actors, or if A is not in actors, I am going to add actors of A with 0. Sorry? Sorry? I can't hear you, I'm sorry. No, I'm sorry. Okay. So, I don't need to really write a way to look up things. This is order of 1. And I am going to add 1 to the actors. Now I'm going to read a name. If name and actors, remember this is a set lookup. I'm going to print Can we do this just to finish the class and then we'll talk about your question? Okay. So, this is the same exact program, except I don't actually have to look things up because now they come for free because I have a dictionary. And every time I have a new actor, I just insert that actor as a key with 0, because if you did not actually have a key, like for example, if you did not have a key, if you say D of 3, it's going to give you a key error. So because of that, the first thing I do is I add the key here. Then I increment by 1. It's the same exact algorithm, except there is no lookup. So this should hopefully work the same exact way. Okay. And if you want to see how fast it runs for the full data, so for 260,000 lines, it's almost no time effort at all, right? So it works the same exact way. So in fact, if I were to analyze this solution, let's go back and do the same thing. In this solution, I go through for every single line in the file, right? So if the line has n lines, for n times, I look up the actor, but since that the lookup is a set operation, it's order of 1. It is not a linear. It doesn't matter how many things are in the list, in the set. So it's order of 1, and this operation is order of 1. So in fact, this is a linear algorithm that I actually only have to do this n times, which is the number of files, number of lines in the file. The previous algorithm, I had to do one thing, order of n, everything in the file, but then I had to sort that, which was n log n, which was a little bit more expensive. Then I did one more pass over the file, which was another order of n. So it was slightly more expensive. And then the first solution was for every line in the file, which is order of n, I actually do another order of n over the list because I have to search things in the list. So that was n squared. Okay? And we are going to go through these kinds of solutions many times. So you will get used to it. If this doesn't feel natural yet, don't worry about it. It's okay. But start to get used to understanding that there is a cost to what kinds of solutions that you choose. Now, in this solution, we happen to just store the number for a given actor. But I could have done many different things. For example, instead of storing the number of movies, I could have just stored the set of movies for the actor. It would actually have been very easy to change that. Okay. Instead of this, I could have created a set of movies for an actor as the value. Then I could have done more interesting things. Like, for example, for every actor, when I find a new actor, I have an empty set. Now, for this actor, I can add the current movie. Okay. Now, instead of looking up how many movies this actor have, I can also print what those movies are. So and I'm going to get rid of this I here. So we can run this. Okay. So if you wanted to see this, this is now reading every single movie by every single actor in the big database. It doesn't only just return this, but it also returns what those movies are. And it was only one line of change, right? It was basically 1 or 2 lines of change. So it does only find 35 movies, which is an interesting thing, but we will figure that out later. Okay? So the point is that dictionaries give you such power that it will take us some time to learn all that we can do with them. And then we will have to think about the complexity of everything we write from this point on. So we will continue doing this starting next Monday again and again every time we write a program. So let's stop here, and then we'll continue from here.